All right, let's just dive right into this. Welcome to the Explainer. Today we're unpacking what I think is absolutely one of the most significant leaps in AI we've seen in a while. Meta's advancements in video-based world models, specifically VJEPA 2 and the brand new VJEPA 2.1. Now, since you're likely familiar with how foundational language models work, you know we've pretty much mastered text. But getting an AI to natively understand physical reality, motion, and spatial depth, that is an entirely different ballgame. Today, we're breaking down the exact architecture and the brilliant algorithmic tweaks that are making this possible. So here's our roadmap. We'll start with a quick intro to world models, decode the JEPA architecture, look at how version 2.1 unlocks dense visual features, benchmark the state-of-the-art data, and then, the really cool part, explore some real-world robotic applications. We are moving straight from architectural theory to empirical physical results. All right, part 1, Introduction to World Models Beyond Text Prediction. To really appreciate what VJEPA 2.1 is doing, we kind of have to zoom out and look at the AI you probably use every single day. You know how standard text LLMs work, right? You feed text into a transformer, and it auto-regressively predicts the next token based on statistical language patterns. Pretty standard stuff. But video world models? They have a much grander challenge. They aren't predicting words. They're predicting actual physical outcomes. They observe video frames and have to anticipate dynamics, gravity, object permanence, spatial relationships, the works. And the kicker? They do this latent space prediction without getting bogged down trying to reconstruct every single literal pixel on a screen. Which brings us to part 2, Decoding the JEPA architecture, or learning by masking. Okay, so the absolute key here is understanding the Joint Embedding Predictive Architecture, JPEA for short. Designed by Jan LeCun and the FAIR team, it's a completely self-supervised framework. It takes an input, say a video, literally masks out a huge chunk of it, and then asks the model to predict what's missing. But here's the genius part. It doesn't predict those missing pixels in the observation space. If it did that, the model would obsess over unpredictable high-frequency noise, like the exact ripple of water in a pond or individual blades of grass blowing in the wind. Instead, JPAA makes its predictions in a learned latent space. It creates a conceptual, abstract understanding of the scene that completely avoids representation collapse.
The sheer scale of the VJEPA 2.1 architecture is incredibly impressive when you look at how the model ingests reality. Older models used to treat static images just like, say, 16-frame videos where nothing moves. Obviously, that's computationally wasteful, and it creates a really bad representational bias. VJEPA 2.1 totally fixes this by using separate modality-specific tokenizers. It has a dedicated 2D convolutional encoder for images and a separate 3D convolutional encoder for video clips.
Let's break that complex process down into 4 digestible steps. Step 1, the input goes through that modality-specific tokenization we literally just talked about, turning images or videos into embeddings. Step 2 is mask corruption, so aggressively dropping patches of information. Step 3, it feeds the remaining visible context tokens and the blank mask tokens into a multi-level predictor. And finally, step 4, a distance-weighted loss is applied. This basically evaluates the model's predictions against the uncorrupted view. This is exactly how the AI learns the rules of the physical world, with 0 human-labeled data required. Moving on to Section 3, Unlocking Dense Visual Features. This is the big jump from VJEPA 2 to 2.1. To get why version 2.1 is such a massive breakthrough, we have to look objectively at where VJEPA 2 fell short. And it had a pretty specific bottleneck. See, VJEPA 2 was amazing at global scene understanding. It knew what was happening overall. But local spatial structure, it was super fragmented. If you asked it to track the specific edge of an object, it just kind of fell apart. Why? Because the training loss was only applied to the masked tokens. The visible context tokens were basically ignored during the loss calculation, so the network just used them as these lazy global aggregators instead of forcing them to preserve the fine-grained local spatial layouts. When researchers map the model's learned patch features to RGB color channels using principal component analysis, it brilliantly illustrates the fix. With the older VJEPA 2, the colors are noisy and fragmented, just a mess of static. But with VJEPA 2.1, suddenly, the colors are spatially coherent. A diving board is completely distinct from the water around it. A cat's features are unified. The AI actually learned to map similar semantic objects to the same components with striking spatial consistency. So how exactly did they achieve that clean mapping? It boils down to 3 major algorithmic innovations in 2.1. First up, dense predictive loss. The loss is now applied to all tokens, not just the masked ones, but the visible ones too. This explicitly grounds every single token in its exact spatial and temporal location. Second, deep self-supervision. They apply this objective hierarchically across the intermediate layers of the encoder, rather than just at the very end. And third, those multimodal tokenizers we touched on earlier, which help the model properly disentangle static appearance from actual temporal motion.
All right, Section 4, benchmarking state-of-the-art performance, the data. Let's look at the hard numbers.
When we translate all that theory into empirical performance, the results are wild. Looking at the relative improvements of V-JEPA 2.1 over its predecessor, the leaps in dense tasks are incredible. We're talking about a 52% improvement in depth estimation and an absolutely staggering 96% improvement in object tracking. By forcing those visible tokens to retain local spatial structure, the model has literally transformed into a powerhouse for highly precise, dense visual tasks while still keeping all its global understanding capabilities.
Drilling down into the specific benchmarks, the numbers are just striking. Take linear probe monocular depth estimation on the NYUV2 dataset, where you want a lower root mean square error. V-JEPA 2.1 drops the error rate from 0.642 all the way down to 0.307. That's huge. And on the EGO40 dataset for short-term anticipation, which essentially measures how well the model predicts exactly where and when an object interaction will happen next, it jumps from 6.02 to 7.71. Think about that for a second. It's not just passively seeing the video, it's accurately forecasting physical interactions before they even occur. Which brings us to this incredibly punchy metric: a 20% absolute improvement in zero-shot real robot grasping success. The upgraded representation space isn't just some theoretical win on static benchmark datasets. It directly translates into massive performance gains when the AI is actually given physical form. And that brings us to our final section, Part 5, Real-World Robotic Applications, Zero-Shot Deployment. To put this to the test, the researchers set up a pretty rigorous physical evaluation. They took the pre-trained V-JEPA 2.1 model and fine-tuned it on just 62 hours of generalized robot data from the Droid dataset. 62 hours is practically nothing in AI time. Then they deployed it on a Franka robot arm with a parallel jaw gripper. But crucially, they tested it zero-shot in entirely new environments. The robot wasn't given any special code telling it how to move its joints. It was simply handed a target goal image and told, hey, figure out the physical path to make reality match this image. When the sequence begins, the Franka robot R approaches an unfamiliar target object, completely zero-shot. Because V-JEPA 2.1 has those highly refined dense features and that state-of-the-art depth estimation we just talked about, the model inherently understands the 3D geometry of the table and the target object. It initiates a reach action without bumping into the surface or misjudging the distance. It is honestly incredible to watch it navigate an unseen environment this smoothly. As the arm moves closer, it precisely aligns the gripper. Now, this requires intense temporal and spatial consistency. Remember those dense, localized features we looked at earlier? That's exactly what allows the model to reason over actions along the precise depth axis of the camera. It knows exactly where the edge of the target is relative to its parallel jaws, constantly updating its spatial grounding frame by frame. And finally, the successful execution of the grasp. It lifts the object flawlessly. This physical interaction right here directly validates all the architectural upgrades of V-JEPA 2.1. By supervising all the tokens and applying that deep self-supervision across intermediate layers, the model developed a world model robust enough to not just analyze video pixels, but to actually orchestrate complex pick-and-place tasks in the messy, completely unpredictable real world. Which leaves us with this final thought. We've spent the last few years watching AI conquer text generation and logical reasoning in the digital realm. But V-JEPA 2.1 represents the bridge to physical embodiment. So, what happens when AI foundation models can observe, reason, and plan in the physical world as effortlessly as we do? With these dense, self-supervised world models, I'd say that reality is arriving a whole lot faster than we thought. Thanks for joining me on this explainer.